Welcome back to MAT052. I'm going to continue along working on the difference between two means. Last time we talked about unpaired data or independent data, and I did want to go back through and clean up one thing before we get started. I was working on this problem, and when I wrote my confidence interval, so over here is the confidence interval, from here we calculated it. We did different degrees of freedom. But when I wrote my result, here was my left endpoint, and I'm going to write 8059 and 12.998. And when I wrote my solution here, I used the symbol mu, and this really should have been mu1 minus mu2, the differences between these two population means. And I just want to clean that up. I just got ahead of myself a little bit. Okay, so let's continue on. We went through all of these. Here was our mummy's curse that we looked at, and we failed to reject H0 on those. How about inferences for paired data? Inferences are basically hypothesis testing and confidence intervals. I use data from a sample to determine information about the population. That's what basically inferences are. I infer something based on the samples. Okay. So when the data consists of matched pairs, we can test hypotheses about the difference between the population's means by computing the difference between the values in each pair of data, and then following the procedure for either hypothesis about a single population mean, basically is what it is. So the assumptions required for a test of a population mean must hold for the population of differences. It just says that if I have that the number of each sample is greater than 30, the number in the differences would be greater than 30. If I had both of them were normally distributed, then the two would be normally distributed, and those differences would follow suit. Okay. So if I have the difference of two means paired data, here's what I'm going to do for the confidence interval. And here I'm going to use a couple of different symbols here. The mu d this is the difference. This is the symbol you're going to use for the difference of population means from mu1 and mu2, but this just says mu d says that these are paired data. Okay, so that's a very special symbol. I'm only going to use it when I'm talking about paired data. So it would be like the same people took some medicine for 6 months. We measured their blood pressure. Then we switched the medicine. The same people did a different medicine for 6 months. We took those, and we're just going to see if the averages of those, the mean of those, should be different. Okay. So D bar would be the mean of the differences, of the sample differences. So we're not going to use x1 bar, x2 bar. So basically I've got a data set x1, x2, and then I'm going to have the differences. I'm going to label this the difference here. So let's just go, this was 7, 5. So the difference would be 7 minus 5 is 2. And let's say 6, 6. So the difference would be 6 minus 6 is 0. And then let's go 5 for this third set, and I would do 5 minus 4 is -1. And what I would do was calculate the average of these things. What would be the average? So I would just add up 2 plus 0 plus -1. So the average would be 1/3, I'm sorry. So this would be 1. 3 items would be 1/3 would be my difference mean of the differences. Okay, and then I would do the standard deviation of this data set, just like I would do 1 var statistics in my calculator, or use Excel. But the standard deviation would be S sub D, the sample standard deviation. Okay. Here would be the test statistics for the difference between two means matched pairs. Here's my S sub D. I'll have to go through this D's, calculate my S sub D. Here's my D bar minus mu 0, and this mu 0 would be my hypothesized mu d value. Okay. So for paired data, we always subtract the second item from the first item. So this is x1 minus x2. Subtract the second one from the first. Then I use the differences of the two values to calculate the mean of those differences and the standard deviation of those differences. If you've got an 84, you could actually put list 1, list 2. This would be like L1. Here's your L2 list. And then in your L3, you could actually go here, just go up to the top and say equals L2 minus L1, and it would do those differences for you. So mu d, this is actually the mean of the differences. This would be the d bar, and then standard deviation of the mean of the differences and the standard deviation of the differences. This is for the population. That mu d would be for the population mean of the differences. We'll see it in just a second. Okay, so here is some data before and after exercise and heart rate. A simple random sample of 7 people embarked on a program of regular aerobic exercise. Their heart rates and beats per minute were measured before and after with the following results. Construct a 95% confidence interval for the mean reduction in heart rate. So this is the before. I want the mean reduction. I want the after. So this would be, here's my x1 is my before, and my x2 would be after. Okay. And I'm hoping that this was going to be a reduction, so it would be a less number. But here I'm going to write these down in this column this way. Before is 81, 84, 79, 85, 79, 84, and 87. This would be 73, 77, 73 again, 78, 71, 75, and then 80. Same person before and after. Okay. Okay. So I want to go and I want to calculate the differences. So here would be 81 minus 73. I'm going to do calculator to make sure I don't do anything off the fly. So this would be 8 for this guy. 84 minus 77 would be 7 for this. Six. Seven. 8. 9. And then 7. Okay, so I'm going to go and I'm going to put this data into my L1 and do the 1-bar statistics. Okay, so that'll give me everything that I need to do in my data. Let me clear data. Okay, now let me get it in there. 8, 7, 6, 7, 8, 9, and then 7. It says I've entered 8, 3, 4, 6, 7. Oh, yeah. Okay, so I've got that correct. And now I'm just going to run the 1-bar statistics on my L1. And this is what I'm going to look for. This is actually going to be the mean of the differences. And then when I do that, my n is equal to 7. I get my x1 at my x bar 7.429. I'm just going to 429, and then my s sub x. This is for sample data. That would be 0.9759. Okay, so that is this guy. And then my S sub D is going to be the 0.9759. Okay. So when I go back up, I need, here's my D bar. This is for my margin, plus or minus T alpha over 2 times SD over the square root of n. So this looks just like the margin of error for a mean when I'm using the standard deviation. So I wanted to do this. All right, it was asking me to do this for 95% CI. Okay. My degrees of freedom is the 7 minus 1, the 6, the number of the data set. And my alpha was 0.05 for a 95. I need 0.05 over 2, which is 0.025. And then if I go back over here, that's what I'm looking for. I'm going to bring this back up. 0.025 for 6. 0.025 for 6 is 2.447. So 2.447. Okay. T alpha over 2 was the 2.447. Okay. My margin of error, SD, 0.9759 over the square root of 7. And this margin of error, so I've got my X bar, 7.429, plus or minus that. And now I'm going to bring this up. That's 7.429 plus or minus this margin of error when I calculate it. And I get 0.90258948, which would give me this interval. So I'm going to do this minus that, 7.429 minus that. .526 less than, now I'm going to use that mu d. This is the differences of the means. The mean of the differences, sorry, the mean of the differences. And then that guy plus. And then that's 8.3316. Like that. So that's how I would write that with the mu d when I'm writing it this way. That way I would understand this is paired data and this the differences of the means. If I calculated the mean of the differences, if I did all of the means and I did the differences, that would be the range that would be in for paired data. Okay, before and after. Okay. So here's a different problem. So the paired data difference of two means following are the annual amounts of rainfall in inches in 6 randomly chosen cities for 2 consecutive years. Can you conclude that the mean rainfall was greater in year 2 than in year 1? Okay. So I'm going to do a little bit differently because I want to do if it was greater. So I want this to be a positive number. If I did it the other way, if I did year 1 minus year 2 and year 2 was greater, I'd actually get a a larger number. So we're going to do a year 2 minus year 1 in this case. You're free to do either one, but you just have to be careful how you interpret the results of increasing and decreasing. Okay, but they're kind of guiding us through, so I'm going to go with what they have. Okay. So let mu d denote the population mean difference, year 2 minus year 1. So state the appropriate null and alternate hypothesis about mu d. So the way we're setting it up is that if this is greater in year 2, this is going to be positive. So we're just saying that that mu d would be a positive number. Year 2, if this is greater than this is mu 2 would be greater, the mu d would be greater than 0, okay? Versus less than or equal to 0. So this would be the differences of those things being positive or increasing. Greater, this would be less than. So this would be our H0 because it's got the equal signs. This would be our H1. We're going to do a right tilt test, and then we could do, okay. What is our test statistic value? That would be the t equals to d bar minus the mu d 0, whatever that thing was, and this thing is just 0 here, and then s sub d over the square root of n. Okay, so this kind of goes away. We don't have to worry about that. Okay, again, there's the 0 that we're talking about. We could claim that this was greater than 3, you know, where the mean difference was greater than 3 inches, and then this would be 3, and we would kind of work that thing through. Okay. So we need d bar and s, so we need the differences between those. I'm going to go through, and I'm just going to do it like this. Here is my year 2, here's my year 1, 34.6 versus 25.1, 18.7 versus 15.3, 42.6, and this was 46.4, 41.3 versus 31.2, 60.6 versus 51.7, and then finally our 29.9. It looks like I'm writing uphill, but it's just my boy the board and the camera set up, and 24.2. So now I'm going to count I'm going to do the differences between 2 and 1, just like they say to do over here, to keep up with what they're doing. So here I'm going to get my stuff going, clear, 34.6 minus 25.1. This is 9.5, 18.7 minus 15.3, 3.4, 42.6 minus 46.4 minus 3.8 in this case, 41.3 minus 31.2. This is 10.1 inches here. 60.6 minus 51.7. 8.9. And then 29.9 minus 24.2. 5.7. So now I want to put these in my L1, add them up, divide by 1, 2, 3, 4, 5, 6, and then do the standard deviation. So I want to put it into L1 and then have everything worked out at the same time. So my data, let me delete all of my stuff from my last adventure. 9.5, 3.4, negative 3.8, 10.1, 8.9, and then 5.7. And then I'm going to do my second stat. Sorry. 1 var. And I get my n is equal to 6, so that's correct. That's what I was expecting. My x bar is 5.6333. Repeat, this is my d bar, so that's what I'm going to refer to that. And then I go down for my sample, my s sub d, which was set s sub x in my calculator, 5.283. And then 057, 054672. Okay. But now I want to go back up here and use this. I've got everything. My T would be my D bar, 5.6333 minus 0. Do this, so that's just going to be this guy, over S sub D, 5.283, parentheses, the square root of 6. Divided by 5.283 divided by and I get a 2.6119 08114, but I'm going to stop at the 4. Okay, so that's the value of our test statistic. Compute the p-value. Let's do that one. Let's compute the p-value. Okay, so what I would want to do, this is a right-tailed test. So I need, here is 2.6119. I want the probability to the right. Okay, so if I go back, I'm going to do, you could do inverse t if you have a calculator, but I'm going to go here and do it. My degrees of freedom is 5, and what I'm going to do is go over here. This happened to align with my right tail. If it was left tail, I kind of do the very same thing, but I just realized this is going to be that I would do a negative number, the positive version. Okay, so I'm going to find 2.6 in here, 6119. So it's between here and here, and I'm going to go up here at, this is my 6, sorry, here's my 6, and I need to go over between the two to find my 2.6119 between here. So here's the area between here and here. So the P value is between 0.025 and 0.01. So 0.01 to bigger to 0.025. That's my p-value, somewhere between there, and I'm going to assume that it is less than here. But we're testing, so that's the best we could do with the table, and it's asking to basic conclusion at alpha. So both of these are less than alpha, which is 0.05. This is the question you're answering. Both of these numbers are less than 0.05, so yes, that's true. And when that's true, we reject H0. How about if I was doing it by regions? This would be 0.05 in here instead of that, and that critical value, I would be able to do the table directly and get a better reading of this. This was my 0.05 in here, 6 degrees of freedom. So this would be 1.943 FTR. This value, 2.619, would be somewhere in here based on that picture, and we would be in the rejection region. So either way, by our p-value or by regions, we would reject H0. We go back up here, we reject this, and rejection is good because if we reject, always rejecting H0, we just go to the other one, and we can conclude that there is a greater than 0. So year 2 is actually greater than year 1 to make this positive. If I subtract year 2 from year one and get a positive values, that implies that this thing actually increased. So there's sufficient evidence at alpha 0.05 that the rainfall increased year two from year one. Okay. All right, so that kind of finishes us up, kind of my examples of the differences between two means. We looked in the earlier video, part one, part A, was independent data. So it could be at different regions, different sample sizes, but if they're paired, it's at this was a year two and a year one, same place, but I just looked at different data between at the same time. Okay, so this would have been at the end of the year two, end of the year one, same place. This would be the only way that this made sense as a paired data. Okay, so hope you found that helpful, and we'll see you guys next week. Have a good day.